Can you hear me? Okay. Okay. So so this is a task. The main task that I did during my PhD was to take the concept of BDT in a level 1 trigger in Atlas and bring it into production into Atlas. And there are multiple challenges along the way. I'm going to address one of them, a particular challenge, and show some code that I wrote that maybe might help someone else with facing the same issue. So first of all, a few words about what is Atlas and what is a trigger and level 1 trigger. So Atlas, you can think of it as a huge digital camera that takes very high resolution pictures, 40 million times a second of colliding particles at its center. And this data is eventually sent to teams of analysts, of physicists, that search for particular patterns. They focus on some pattern. They, very simplistically, they count the number of times they see that pattern in the experiment, compare it to theory, and if there's like a discrepancy, then there's something interesting going on, and you should investigate further. Ideally, we would take everything and give it to the physicists to analyze, but we cannot really, because the downstream systems cannot really handle that much information. So the trigger's job is to select the most interesting events, the most interesting pictures, and throw away everything else. And this must be done from 40 million times pictures per second. It must be reduced to around 1,000 pictures per second. That is done in 2 stages. First stage is a level 1 trigger, which is a hardware-based trigger. And the reason it's hardware-based because it needs to tick along with the collision rate 40 million times a second, so it's FPGA-based. And then the resulting 100,000 events per second are sent to a high-level trigger, which is software-based, so it's able to run more elaborate algorithms slower. And then eventually it ends up with 1,000 events, interesting events per second. The algorithm that I worked on lives in a subsystem of the level 1 trigger, which is called the level 1 calorimeter trigger. A calorimeter is a subsystem of Atlas that measures the energies deposited by particles passing through it. And the image that the algorithms that live in that system see are seen on the top right there. So this is like the structure is a structure of cells, and it has multiple layers. So this is an example of how an electron of a specific energy, 70 GeV electron, would look like in a calorimeter. But in our case, I was focusing on the tau lepton particle. So this thing runs in the effects, which is another subsystem of the L1 Calo subsystem of the trigger. In the effects subsystem, it has 24 modules like this. Each module has 4 FPGAs. It covers the entire calorimeter. And each of those FPGAs runs 8 instances of this identification algorithm that needs to identify this tau lepton. And each instance looks at a fixed, small, tiny region in the calorimeter that is similar to the one shown on the top there. These algorithms, they run at the 200 megahertz domain, and everything must be fully pipelined. So it must, every 5 nanoseconds, it must produce, except the next image like that, and after about 12 clock cycles, exactly 12 clock cycles, produce the output, whether it sees a tau or not. So the people who are familiar with machine learning look at the picture in the previous slide, and it screams machine learning because probably it's more performant than anything heuristic-based. So in high-energy physics, we have generally 2 kinds. First of all, I don't know if anyone didn't yet understand what machine learning is, and for some reason, those are trainable pieces of computer code that accept features, and they produce decisions based on those features. And they are usually better than heuristic algorithms at identifying objects in fuzzy settings like cats in images or particles in the noisy environment of Atlas experiment. There are 2 kinds in high-energy physics, commonly used models, the neural network and the boost decision tree. So the neural network, it was already shown in some good presentations before me. It's based on the workings of the brain, and it has neurons, but it's usually more performant if you give it enough resources. It can accept very basic features, it can figure out on itself which, what to look at in those features. As I think I already said, that it's heavy on resources. It has lots of architecture, so it's actually difficult to hone in on a good architecture to really do the job in an optimal way. But they have probably the highest performance compared to other models. On the other hand, there's the boosted decision tree, which is based on applying cuts on features of the input vectors. These features are engineered, so it's kind of an assisted machine learning. It is light on resources compared to neural networks, and it is parallelizable on FPGAs, and I think you'll hear much more about it in Shioni's talk about Conifer. And so it's super fast to evaluate, and the performance is often not far from neural networks. So just to put in perspective the amount of streaming data rate that we need to handle in this algorithm versus the latency requirement. So this is an image of all the modern algorithms and how much data they need to handle, the volumes of data. So the LHC Level-1 trigger, the blue big sphere, the size of the sphere is how much yearly volume of data it should handle. So it's at the lowest inside the FPGA range, the pink rectangle. So it needs to, it has the highest standards to live up to. And our algorithm is marked by X. It's supposed to handle about 40 gigabytes per second, and it's supposed to return an answer after 60 nanoseconds. So at 200 megahertz, 12 clock cycles. So how do we take something, a model like machine learning, like a neural network or VDT, and we place it on an FPGA? So there are multiple tools in existence. Several of them are listed here. HLS-generated BDT, Conifer, firmware ex machina. So the idea is to take a Python-trained module and to feed it into one of these tools, and then they will eventually generate RTL code that can be used to generate a design on an FPGA. And it often involves an intermediate step of converting to C++ code and feeding it into a high-level synthesis tool. In our case, the chips were Vivado, were Xilinx, Virtex 7 chips, so the Vitis HLS toolkit was used. So just now to understand what is the flow in our case. So first we start with an XGBoost Python-trained model, and then it's fed into Conifer. Conifer has several backends, and I chose to use the Xilinx backend because it produced from the latency perspective the most quick design. And it produces an RTL code that looks something like that on the top. It's a really unreadable blob of code that needs to be kind of somehow stuffed into a really nice, harmonious effects firmware. And so this question mark was the big challenge, was how to do that and eventually put it in a production environment and make it work. So to get more technical, this is the greater tau identification algorithm. Only a part of it is a BDT. So the blue rectangle marks what is the BDT. So it has input variables in the yellow boxes, and the BDT itself is the green box. On the top, by the way, is the clock cycles. And the orange boxes are not, the bottom orange box is done completely in parallel. It's not related to BDT evaluation in any way. And the right box takes the BDT score and compares it against a threshold. So this is how the greater algorithm looks like, and where the BDT part, the HLS-generated part sits, it sits in this BDT box there. So to summarize the requirements, so the overall latency constraint is 12 clock cycles at 200 megahertz. It must be fully pipelined, and we must be very flexible. I will talk more about the flexibility, what exactly it means, because R&D, research and development, happens in parallel to the development of this algorithm. And so one simplifying thing was that there was already in place an algorithm that is heuristic space, and this algorithm was meant to switch it out. So the interface was really well defined. So that was a very simplifying thing. About the flexibility, so we expected that retraining would be very likely. So that would change the BDT design's latency. We also expected that the BDT variables might change. So there needs to be flexibility in how the variables are computed. And we also must not neglect the simulation, which always must reflect what the VHDL, or the firmware version does. So how do the BDT variables look? So this is the image similar to the one that I showed of the calorimeter. And the raw inputs to the greater tau algorithm is 99 cells like this. The actual name is supercells, but I'll use the word cells just for simplicity. Each one of those rectangles in this diagram is a 16-bit logic vector, is one cell. And the variables are summations, are simple summations over same colored cells. So there are 11 variables in total, 10 are listed here, and one more variable, which is a sum over more cells, which is a sum over the center region of this object. So the variables are, the rest of the variables, not this big one, are sums of at most 4 cells. So it's 2-stage adders, assuming that the adder accepts 2 inputs and produces an output after 1 clock cycle. So that's 2 cycles to evaluate. But what if we want more elaborate variables? What if the performance studies show that we need better variables, like, for example, these? And this is an actual iteration that we had. And, for example, these variables, the red ones, those are 8 numbers. Okay, so the summation of 8 numbers and not 4, so that's a 3-stage sum. So to summarize, the raw input is 99 16-bit numbers, of which we should be able to pick n subsets of varying size, and everything needs to be configurable. All of them must be ready at the same cycle, so those that are not ready must be delayed. And this is expected to be very dynamic and to change many times. And the BDT RTL as well, the structure parameters or the hyperparameters of the BDT might change. And that would affect, of course, the latency. So and because the BDT score is used downstream, that the other signals that are supposed to be ready at the same time should be delayed. Yes. So the way I decided to tackle this is, of course, automation. There's can't think of another way. So the XGBoost trained model is fed into this automatic pipeline. The automatic part consists of the Conifer tool, which produces a VHDL RTL of BDT. Then this is fed into a VHDL code generator along with a JSON file that describes the summation schema of the variables. And this produces a VHDL of the great tau algorithm, the greater tau algorithm. And this is placed inside a test bench along with a simulation, which also automatically is ensured to reflect the firmware. And then the input data is fed into it, and the outputs are compared so that this is tested. And this is then placed into the existing eFax firmware by just copying files into the repository. And eventually, there's a hardware test that, unfortunately, was not automatizable. So the main component of how I did this was this adder tree that I came up with, which is based on the NetworkX package in Python. So just a simple example. So let's say we want to compute 3 sums, A, B, and C, and we have 3 inputs, X, Y, Z, and the sums should look like this. We can specify that the output cycle, A should be ready whenever it's ready, we don't care. B should be ready at 8, cycle 8, C should be ready at cycle 7. And also the inputs can be available at different cycles. So X ready at 0, Y at 1, Z at 3. So then this generates this kind of graph behind the scenes. Then it adds, the graph represents the summation. So A accepts X, Y, Z. I'm sorry, maybe people don't see it, but then latencies are computed, and this is expanded to a graph like this, and then eventually you can generate automatically this fully pipelined VHDL for all the additions and delays. Just to focus on a few paths here. So so each orange node is an adder that accepts n inputs and produces an output after log base 2 n cycles. And A, for example, here is not specified when it should be ready, so it's ready whenever it is, which is 2, because it accepts 3 inputs, so it's ready 2 cycles after. So it's in these dark green circles. And then here, for example, C, another example. So C is ready after, so here it's ready, 1 clock cycle after, because it accepts 2 inputs, Z and Y. But it needs to be delayed to cycle 7, so it's actually ready at cycle 7. And all this is automatically generated in VHDL code, which looks something like this. I'm particularly proud of this comment, because there is this table at the end that shows exactly when the outputs are ready, and this really helped debug things. So it shows everything, the sums and the inputs and the outputs. Then this is how the VHDL actually looks. So this is the entity adder tree. It has a clock input. It has 3 ABC, 3 input words for XYZ for the inputs. Outwards is 3 data words. Data word is a 16-bit logic vector, and the overflows. Then there are definitions of signals, also automatically generated names. And the inside, the internal implementation is based on these 2 entities, multi-adder with carry and delay with carry, which are heavily based on multi-adder and delay, which already exist in the effects firmware implemented by Francesco. And for example, this this path of Z to C to the output is implemented this way. So you have 2 inputs. You have Z, which is directly fed into this multi-adder. Then you have this delayed Y, which is fed into C. And then the output, this output goes as an input to this delay and is produced after 3 clock cycles. And then eventually it's read out into the outputs. This is usage. I won't go over it. If you are interested, you can go to the link in the 2 slides and try this out. This works. So just final slide before I finish. More pipeline functionality is not the only thing the pipeline does. So we need to also compute the delays automatically based on the generated BDT RTL latency. We need to generate the configuration file for the simulation, which contains both the BDT model and as well as the summation schema, and also other sums that needs to be computed in the greater tau algorithm. This full algorithm is run in the Vivado XSIM test bench and compared with simulation on a real data sample, a real Atlas sample, and also on fuzzing data, randomly generated data. So to summarize, machine learning models are very desirable in these complex environments, and the BDT model is operational currently at the Level 1 trigger and Atlas. And there were many challenges that really humbled me from having this concept of having a BDT and eventually having a much simpler version of what I had in mind. So the challenge is that it mainly must be very flexible, and that automation is therefore crucial to really be able to implement it. And I showed you this package that I wrote, the adder tree. It's accessible here. It's not really open source, as in has a license and everything, but you can browse the code. And the full pipeline is accessible also here in this last link. Well, thank you very much.
Thank you, David. I see we already have a hands up.
Thank you for the presentation. So just for that I can understand, you are using machine learning to increase the capacity of streaming more events and make a decision, a faster decision for your trigger, right? But then you add for doing this, you add an extra layer of HDL that is called BDL HDL, right? This binary tree HDL, and then in my opinion, if I feel maybe it's dumb, but as per my understanding that if I would have written simple VHDL LHS code, simple VHDL code, right, and use that as a trigger, right, it would, and without any extra HDL layer, right, maybe that would have been faster, or why this machine learning thing, if you need to even add it, this also adds an extra HLS layer, which I don't know if it's very productive. So.
Yeah, so you should keep in mind that I came into this project not knowing VHDL at all. I'm a software developer originally, so HLS was I felt at home in HLS. And also Conifer, so it has, maybe you'll hear it from Shioni, but it has two backends. So there's this exciting backend which is the HLS, and there's another backend which is the VHDL backend which directly generates VHDL code. But from my experiments with the VHDL backend, it just produced a it took too long to evaluate the BDT when using the VHDL backend as opposed to the HLS backend. So I ended up using the HLS backend, and you know, the people that were responsible for the code, they were okay with this. So yeah.
Hi. My question is probably answered with regards to its auto-generated code, but all the signals had a default value assigned to them, mostly 0. Is that intentional, or is that just the output of the tool, and you don't have any requirement to default the values?
I think there is no requirement to default the values, but yeah, I was just trying to be safe. So initialize the variables like you do in C++.
Yeah, so I suppose it probably represents what the FPGA is first configured with, but what it might hide is if you reset, you've got a reset circuit, I'm sure, so if you reset the design later on, but in simulation you've only tested the initialized values until you finish your test, you might find that certain values haven't been reset to the value you expect. So it could hide bugs, I guess, would be my thoughts.
Okay. It didn't come up in our test, so yeah, I actually didn't think about it.
Just something to consider, because...
It could be an issue, yeah.
Yeah, the first... so how it's programmed at startup will be different to how it operates in the future when you press the reset button.
Yeah. Okay, thank you for the comment.
Question here?
Yeah, I had a question about your requirements on slide 9. I can say it out, you don't need to go. You say it's 12 cycles at 200 megahertz. That's really short. Why is it? Like, it's fully pipelined, right? So yes. Why do you care so much about such short latency?
Well, the whole system depends on there are other components, not just this component, not just the tau algorithm. There is an algorithm that detects photons and electrons that runs in parallel. So everything must be ready after 12 cycles. That's the design of the system I was introduced to. So I had to stick within the 12 cycles.
Okay, so it's within the FPGA that those cycles are required, not because of some downstream requirement.
I think there are other things that work in parallel to this effect system as well. They also expect things to be ready. Everything has to be ready at the proper clock cycle. So for this case, it was 12 cycles.
Okay, thanks.
More questions? Okay, if not, let's thank David. Okay.